Alright, thanks for watching. And in linear algebra, there's a very classical exercise where you have to find a basis for the null space, a basis for the column space, and the rank of a matrix. And I'm sure when you did that exercise, you had no idea why this works. Well, I have some good news. In this video, I'll finally explain you why this works, because we have enough linear algebra knowledge to actually tackle that. So, what is that mysterious exercise I'm talking about? Suppose A is the matrix 2, 3, 2, minus 6, minus 4, minus 6, 9, 7, 6, 0, 2, minus 6, and 0, 0, 1. And suppose you can row reduce this to get the following reduced row echelon form. Let's say 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 4, 2, 0, and 0, 0, 1. So you don't have to have it in reduced row echelon form, but it makes life easier. And the first question is, let's find the rank of our matrix. So the way you usually do this in linear algebra, you're like, oh, let's just count the number of pivots. Here we have 3 pivots. And in fact, you say, oh, the rank of A equals 3. But the question is, why is that true? And in fact, I'm claiming that the rank of A is equal to the number of pivots. And by the way, for the definition of the rank, you're welcome to use any definition you like, except number of pivots. So some people define it as the dimension of the range of the linear transformation LA, or in another video I showed this is equivalent to saying the dimension of the column space of A. So using this definition, how come that the rank of A is the number of pivots of A? Here's why. First of all, remember we row reduced A to get A prime, and in another video I showed that row reduction precisely preserves the rank, because you're just multiplying by a bunch of invertible matrices called elementary matrices. So, in particular, because row reduction preserves the rank, we have the rank of A equals to the rank of A prime. Equals rank of A prime, because row reduction preserves rank. Which is good, because instead of finding the rank of this complicated matrix, you just need to find the rank of this easier matrix. But, well, in fact, the rank here is so easy, you can find it. So the rank of A prime, that is, by definition, the dimension of the column space of A prime. And what is the column space? You literally just take the span of the columns of A. So basically the rank is a dimension of the span of 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 4, 2, 0, and 0, 0, 1. Close that parentheses. Alright, but notice, in this span, there are a bunch of redundant vectors. Because, for example, minus 2, 0, 0, that is a multiple of this vector. It's minus 2 times 1, 0, 0, which means we can play math Jenga and safely remove it from the span. Because the idea is you can always take out linearly dependent vectors more or less from your span, and this one is kind of essential. You cannot write it in terms of this, But lastly, notice minus 4, 2. It's minus 4 times this vector plus 2 times this vector. So this one is also redundant. And in particular, this is always true for non-pivot columns, just by the nature of reduced row echelon form. Because you have this triangular matrix, sort of, I mean, it's not triangular, but it's like a cliff-like matrix, you always get the non-pivot columns here. The second one is a multiple of that pivot column, or this one is a linear combo of the other pivot columns. Because otherwise they would be pivot columns themselves, basically. So then what you get is the dimension of this span is just the dimension of the span of how many vectors? Well, precisely 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. So interestingly, the column space of A prime is just the span of the pivot columns, which is always true. So in particular, what do we have? The rank of A is the dimension of that span. Those vectors, well, they span the span by definition, and those are those are linearly independent, so the dimension of this span is just 3, because the basis for that span is just those 3 vectors. So indeed, what do we get? The rank of A prime, which is 3, which is exactly the number of pivot columns, which is the number of pivots, is equal to the rank of A. So just to conclude, rank of A equals rank of A prime equals 3 equals number of pivot columns. And because there's exactly one pivot in every pivot column, that equals to the number of pivots. So this is why the rank of A is equal to the number of pivots of A. So that settles one important question we had. Now, here comes the next one. Well, we found the rank. Now what about the dimension of the column space? So, and in fact, let's find a basis for the column space of A. Okay. And how do you do this? So remember, first of all, you figure out where the pivot columns are. So here in this case, the first, third, and the fifth columns. And what you do then is you have to go back to your original matrix, because row reduction, it destroys the span. But somehow the trick is go to the first, third, and fifth columns and pick those vectors, and ta-da! They give you the span and the basis for the column space of A. And the whole point now is to figure out why this is true. So here, namely, so claim if you want. Now I realize I didn't notice that I'm writing in black pen and red pen. It's not pure coincidence. Also, shout out to black pen, red pen. He's awesome. So claim the pivot columns, not of A prime, but of A, form a basis. For the column space of A. So here, we get that precisely 232, 976, and 001 is a basis for the column space of A. And those are precisely the columns 1, 3, 5 of A. Okay. And the claim of this is kind of cute, the proof of this. So why is that true? It depends purely on linear algebra. Not because it's a linear algebra course, but it's very like, uses stuff from like abstract theory, namely with vector spaces and stuff. Because in question A, we actually found the dimension of that column space. So, and in particular, because we found the dimension of this, it'll make life much easier because we know that the dimension of this is 3. Because by definition, the dimension of the column space of A, it's the rank of A equals 3. And in particular, if you have a 3-dimensional space, to find a basis, it's enough to find 3 linearly independent vectors. Because there's this beautiful theorem called the Replacement Theorem that essentially says if you have 3 linearly independent vectors in a 3-dimensional space, they also have to span your space, and in particular be a basis. So because this is true, it's enough to find 3 linearly independent vectors in your column space. And let's use blue, why not? This is very important, so let's call it star. So it's very important. Once you find 3 linearly independent vectors, you're done, because they give you your basis. Now, unfortunately, I need this matrix, so we have to work in this small space, but it's okay, because the proof isn't too long. Because what do we know? Look at the pivot columns. Let's call them W1, W3, W5. Well, look, W1 is just 1 and a bunch of zeros. W3, it's 0, 1 and bunch of zeros. W5 is 0, 0, 1. And in particular, just by inspection, it's clear that those vectors are linearly independent. And this will always be true for pivot columns, definitely in reduced row echelon form, because the pivot columns are just zeros and bunch of ones. And even for row echelon form, because of the triangular nature, the pivot columns will also be linearly independent. So we know that those columns are linearly independent. 1, 0, and W5, which is 0, 0, 1, are linearly independent. That's one thing. Second of all, because the problem is this deals with the reduced row echelon form. What about the original columns? Remember, there's an easy way of going from A to A prime just by row reducing. And since row reduction can be expressed in terms of a matrix, we also know that A prime, it's some invertible matrix times A. In other words, if you start with A and apply the matrix of row operations to it, you get the reduced row echelon form. That's for some invertible matrix B. And in particular, if you call the columns V1, V2, V3, V4, V5, and then W1, W2, W3, W4, W5, what you know, remember this little fact, we also know that W1, W2 up to W5 equals V times V1 V5. Now, remember there's this nice distributive properties of matrices. You can literally take B and distribute it over the columns. Then what you get, W1 up to W5 equals BV1 up to BV5, which tells you that the jth column of A prime is B times the jth column of A. So Wj equals BVJ for all j. And it turns out this will help us find 3 linearly independent vectors because we know the following. So in particular, if you consider, let's say, B applied to those 3 vectors here, v1, v3, v5, bv1, bv3, bv5, well, by definition, they give you w1, w3, w5. Those are linearly independent. It gives you this, and we know this set is linearly independent because it's just 1, 0, 0, 0, 1, 0, 0, 0, 1. And now comes an important fact for today. If you apply an invertible matrix to a set, it preserves linear independence. In particular, what do we know? Here's a fact. If B is invertible, then the output BV1, BV3, BV5 is linearly independent if and only if the original vectors are linearly independent. And I prove this very soon, but let me first tell you how to conclude. We know that those 3 vectors, BV1, BV3, BV5, are linearly independent. So by this fact, V1, V3, V5, so the original columns are also linearly independent. V5, which are precisely 2, 3, 2, 9, 7, 6, and 0, 0, 1. And again, those are the pivot columns of A. So not of A prime, but of A is linearly independent. And look, how many vectors are in there? Well, precisely 3, which is the number of pivots. And remember, that was our goal. It was enough to find 3 linearly independent vectors in column of A. So, in the end, those 3 pivot columns of A, they form a basis for the column space. And this is why you have to go back to the original columns to find a basis for this. Because we know that the pivot columns of the row-reduced matrix, they're linearly independent by inspection. And then going back, so applying this invertible matrix back, you get that the original pivot columns are also linearly independent. Okay, and before I continue, so let's just prove this little fact. It's very cute. First, let's prove this direction. So suppose this is linearly independent. You want to show this is linearly independent. How do you show this set is linearly independent? Well, suppose AV1 plus BV2 plus CV3 equals to the 0 vector, and you want to show those coefficients are 0. Now, because you have info about the matrix B, let's just apply B to this equation. BAV1 plus BV2 plus CV3 equals B applied to the 0 vector, and that is the 0 vector. But now you can just distribute ABV1 plus BBV2 plus CBV3 is the 0 vector. But you see, you know those are linearly independent. And therefore you get that A, B, and C are 0. And here, we didn't use the invertibility. So this is always true for any matrix. If this output is linearly independent, then the input is. What's slightly less obvious is the opposite. So suppose this is linearly independent, you want to show this is linearly independent. So in this case, suppose A BV1 plus B BV2 plus C BV3 is the 0 vector, then you can write it as A BV1 plus BV2 plus CV3 equals to the 0 vector. Now B is invertible, so multiply by B inverse. And you get, this is the identity, so AV1 plus BV2 plus CV3 is the 0 vector. And because now you know this is linearly independent, you do get ABC equals 0. So in fact, this is true. And this had to do with what's called this had to do with linear in the column space and the rank. Now let's move on to the null space. And by the way, so here I did it with linear independence, but also notice that the linear dependence relations are also preserved. Here I realized it was a small mistake, but notice in particular because the second column is minus 2 times the first column, this column should also be minus 2 times the first column. So maybe this minus 6 should be a minus 9 or something. But in general, the linear dependence relations are also preserved. All right, but anyway, let's move on to the null space. So first of all, let's find the dimension of the null space. And the cool thing is we can do this without finding the null space explicitly. So let's find the dimension of the null space. And for this, we need a theorem that relates the null space with the column space. And that's precisely what's called the rank nullity theorem. Rank nullity theorem tells us that the dimension of the null space and the rank, they kind of balance out. Namely, the dimension of the null space of A plus the rank of A equals to the total number of columns, which is 5 in this case. Or in general, it's n, where n is the number of columns. And by the way, I stated that and proved that for linear transformations in abstract vector spaces, the same thing happens for matrices. So in particular, what is the null space here? Well, it's 5 minus the rank of A. And that is something 5 minus 3, which is 2. And it turns out this is very important to figure out what the null space is. So remember now the dimension, the null space of A is 2-dimensional. And now let's find a basis. For the null space. And I have to tell you, to show that find a basis for the null space, you just row reduce and solve this equation. I've done this many times, at least 100 times, and I'm not gonna do it in a video 100 times. No. And what always surprised me is why does row reduction automatically give you a basis? In other words, why, when you row reduce, the vectors for the null space are linearly independent? And I've done this many, at least for 12 years or something, and I realized, actually a week ago, I was thinking about this the wrong way. Because I always thought of it in terms of linear independence. But the whole time I should have thought about that in terms of span. Because it turns out, in terms of span, it's actually much easier to figure out why it's a basis. Because since the null space of A is 2-dimensional, is 2. We don't need to find 2 linearly independent vectors to find a basis. It's enough to find 2 spanning vectors. Because there's this other consequence of the replacement theorem that says if you have an n-dimensional space and you have n spanning vectors, those vectors have to be linearly independent. In other words, a basis is kind of like the smallest spanning set you have. So enough to find two spanning vectors. In the null space. So you see, the whole time, don't think about this in terms of linear independence, because that's kind of harder to show that the vectors you get are linearly independent. It's much easier to show that your vectors span the null space. And in particular, there's a video I've made about Gaussian elimination where I said the wonderful thing about row reduction is that it preserves the solutions. So really, instead of solving ax equals 0, it's enough to solve a prime x equals 0. So since row reduction preserves solutions, we get that the null space of A equals to the null space of A prime. So instead of solving this equation, you just need to solve this equation, and I can finally erase the matrix because we don't need it anymore. So solve A prime x equals 0, which gives you 1, 0, 0, minus 2, 0, 0, 0, 1, 0, minus 4, 2, 0, 0, 0, 1, and 0, 0, 0. Now, because it's already in reduced row echelon form, it's actually not too bad to solve it. And remember this. So let's solve this. What we get is x1 minus 2x2 minus 4x4 equals 0. And then x3 plus 2x4 equals 0, and x5 equals 0, which tells you x1, it's 2x2 plus 4x4, x3, it's minus 2x4, and x5 is 0. And notice in particular, just by the form of the reduced row echelon form, the non-pivot variables, which are x2 and x4, will always be the free variables, because the way the RREF works is that you solve for your pivot variables, so here x1 and x3 and x5, in terms of your non-pivot variables. So those will be free, and in particular they will be the parameters for a null space, because then x, which is x1, x2, x3, x4, x5, equals, again, 2x2 plus 4x4 minus 2x4, sorry, x2 minus 2x4, still, no, actually, never mind, I don't know why I was mad at myself. That was correct, 2x4, x4, and 0, and you can write this as x2 times 2, 1, 0, 0, 0, plus x4 times 4, 0, minus 2, 1, 0. And so, what do we know? The null space of A, which is the null space of A prime, is precisely the span of those two vectors. 2, 1, 0, 0, 0, and 4, 0, minus 2, 1, 0. And again, notice those vectors are linearly independent, and that's not a surprise, because remember, we know the null space is two-dimensional, so it's enough to find two spanning vectors. So notice we do have two vectors here that span the null space, so automatically, by the beauty of linear algebra, we know that it shows that we have a basis for the null space. So our basis is simply those two vectors. And by the way, why will we always find the correct number of vectors? Because of, remember that the non-pivot variables, they're free variables. So in fact, we will find always exactly as many vectors as the dimension of the null space of A. So in particular, we are done. We found a basis for the null space of A. So, and this is why this method always works. So just to summarize, in this case, the non-pivot columns, as I said, correspond to the free variables. The dimension of the null space is the number of the free variables. And lastly, one little teaser, I guess not teaser, but I'll do something different in another video. If we have a pivot in every column of A, this implies, well, the null space doesn't have any free variables, so the null space is the zero vector. And you may wonder, well, what happens if there's a pivot in every row? That's the point of another video. So, little cliffhanger, even though I may have posted the video already, but we'll see. Alright, so hopefully your minds are cleared up now, and now you can just apply this technique in peace. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.